Alright, so today we're going to talk about rational functions. They're a popular topic in Algebra 2 and pre-calculus classes right now, and there are a number of rules that are associated with the way that you graph them. So we're going to go through those rules, and we'll explain a little bit about how they work. So first of all, we'll start with the definition. A rational function is any function that has a variable in the denominator. So I'll write out a few examples here so we can get a feel for it. So we might have something like f of x equals 2 over x. You might have something that looks a little more complex. F of x equals 3x squared divided by 2x to the third plus 9. It doesn't really matter what it looks like so long as they share a variable in the bottom of the fraction. That's what makes something a rational function. So what's unique about these functions is that they look special. They have a particular way that they plot out. They have vertical and horizontal asymptotes. So a vertical asymptote, we draw it in a graph as a dashed line, which I'm going to highlight in yellow here. It's an x value that makes the denominator, or the bottom of the fraction, equivalent to 0. And you might notice that when the x values get particularly close to the value that makes the denominator 0, the y values become particularly large or particularly small. So as we're coming in from the right, my y values go up towards infinity. As I'm coming in from the left, my y values go down to negative infinity. Horizontal asymptotes are a little bit different. I'm going to highlight them in orange. My horizontal asymptote I also draw in with a dashed line, and it's a particular height value that the graph gets very, very close to reaching but never quite touches. So as my x values, I'm going away from the vertical asymptote, as my x values get very, very large, my graph approaches my horizontal asymptote but doesn't quite touch it. Same thing in reverse as my x values become very, very small. I write the equation of a horizontal asymptote in the form of y equals, and in this case the horizontal asymptote is at y equals 1. I'll do the equation for the vertical asymptote in yellow. My vertical asymptotes always have the equation of x equals, and in this case it's x equals 6. So that is the difference between a vertical and horizontal asymptote. So if I want to learn how to graph these functions, the first thing I need to do is find out where I want to plot the horizontal asymptote. And the way that I do that is I have to compare the degree of the top of the fraction to the bottom of the fraction. So we'll do a number of example problems to find out what that looks like. This is the first in the set of many rules in graphing these sorts of functions. So I wrote over here on the left-hand side a standard form graph. So these variables, c, d, t, b, and v, just represent numbers that you'll normally see in regular rational functions. So I'm going to use this function down here as an example. We're going to match each of the variables to actual numbers. So the c value here represents the coefficient tied to the x value on the top. So the c in my actual function would be 2. The d represents the coefficient tied to the variable with the highest exponent in the denominator. So in this case it would be 3. T represents the highest exponent number in the top, so in this case it's 2. B represents the highest exponent number in the bottom, in this case also 2. And V represents a vertical shift value. It's any number that's added or subtracted outside of the fraction. In this case there is no V value, so I can write it in as a plus 0. We won't encounter the C, D, and V values until the next video, but we are going to talk about T and B. So first thing I want to do is I want to compare t and b of both the top and the bottom. So I'm going to do that in this first example. There is no variable in the top, so I'm going to draw one in. Whenever there's no variable, you can draw it in and add it in with an exponent of 0. So I'm going to do that here. So the degree of the top is 0. The degree of the bottom is the exponent number of the variable with the highest exponent value in the bottom. It's 1. So in this case, I'm comparing them 0 on the top, 1 on the bottom. In the next example down, the t value is a 2, and the b value in the bottom is also a 2. So they're the same. So we're going to pick back up in the next video with a few more examples, and then we'll talk a little bit about why it's important to determine the difference between the degree of the top and the degree of the bottom.